This is NeuroLingo, and we are trying to optimize language learning as it is a process that requires intense focus, consistency, and commitment. While trying to tackle this complex issue, it is important that the user studies in an efficient manner that maximizes their progress and time. NeuroLingo enables the user to study efficiently by statistically identifying the words that the user knows versus the ones that they don't know. This is an EEG-based assistive technology that optimizes language learning through improving time management.
Our project analyzes the N400 ERP component, which is commonly used for processing stimuli such as words or pictures. And so what we're able to do is we can deduce whether a word has meaning or does not have meaning within the user, and this directly corresponds to whether they know the word or do not know the word. And so in order to evoke the most clear N400 signal, we're targeting our electrodes for areas involved with language comprehension, nonverbal communication, and syntactic processing. And this corresponds with the left frontal, left parietal, and temporal lobes.
Before we start our machine learning model process, we have to pre-process the data as explained before. We have several hundred combinations of the parameters we set for pre-processing. And after each one, we get a bin of ERP readings related to your brain signals when you do understand a stimuli versus when you don't understand it. After getting those bins, we have to label them because we're using supervised machine learning models. And after labeling that data, we have to use the 80-20 standard train test split, in which 80% is reserved for training the data and 20% is reserved for testing that data. Next, for each pre-processing parameter, we tested it on several machine learning models, including SVM, linear, polynomial, and RBF, KNN, and neural nets. But what we found was that the most accurate model for us was random forest. And to put it briefly, random forest utilizes a sort of wisdom of the crowd, in which each tree represents a unique set of decisions made by the model, and the final result is what the majority of those trees said, hence a forest. After such model was used, we found that the highest accuracy that we got was 70%, which may not seem like a lot, but is reflective of the study that we based our experiment off of, as well as other studies that use ERP readings for their machine learning models.
Through our projects, we use an open BCI Zyklon board and dongle to stream data from 10 channels, including ground and reference electrodes. In our experimental procedure, we modeled a traditional flashcard learning process by tasking participants with learning 60 in-part characters as new words, which we tested on later. Characters were learned in 5 sets of 12 words each. In each test set, participants were shown one word at a time alongside its corresponding translation. Then a test was taken which displayed each word that was from the learning set. During these tests, data was collected in 1,000 millisecond epochs, which immediately followed the testing stimuli. The learning plus testing combo repeated around 5 times, ensuring there was a break in between each set for the participants. Overall, we tested around 7 participants with an average age of 20 and ensured that they had no prior experience of in-part script.
To better understand what our machine learning model is classifying, we visualize the data using Python's ME package. We first remove bad channels using ICA artifact removal, and then we use PCA to look at trends in our data. In the first graph, we see time on the x-axis relative to the onset of a symbol at 0 seconds. And then we see microvolts on the y-axis, with each line representing a channel in our 8-electrode setup. As you can see, coming from 2 channels, we see a negative deflection at 400 milliseconds. In the second graph, we see the difference between the understood words and the not understood words. This gives us an idea of the theoretical distinction between these 2 classes, most notably a negative deflection at 400 milliseconds.
So we found that we can reliably distinguish between brain activity for knowing the meaning of an artificial language symbol and not knowing the meaning, and this was mainly due to the N400 reading. However, our project did have a few limitations. For example, the study that we used as a reference used the 10 to 20 electrode setup, but we used the 8 electrode setup. And because we were only able to test 7 participants, we did notice that there was a strong bias towards the learned stimuli. But overall, our project specifically focuses on learning a new language using different methods. And what makes our project especially unique is because it focuses on accessibility through a hands-free design. So this makes it more inclusive for a larger group of people, including those with limited mobility or dexterity. And by eliminating the need for this manual interaction like existing language learning applications use, we make the learning process more efficient and seamless for users.